15 years or so now. Um, Sorry, unfortunately, as the let me get rid of that. Yeah, for around about 15 years now. I've been probably well known in the LVM community for LVM Weekly, which is a weekly newsletter I'll mention later, which I've been running for about 11 years now. And maybe the biggest piece of upstream work I've done is initiating the upstream RISC-V LVM backend. I'm going to assume everybody has some degree of familiarity coming to this presentation with compilers in general, and maybe what is LVM and Clang. But it's a pretty big project these days, so I'll just highlight a few things about what's included because it can be hard to keep up even for people who are actively hacking on Clang and LVM day in, day out. So it's a, it's perhaps best known for its C and C++ front end, Clang, which many of you may have used already. Maybe the second thing that's most well known about it is LVMIR, its intermediate representation, and all of the middle end optimization passes based around that that provide a relatively easy to modify and extend way of implementing compiler optimizations. As highlighted here on this slide, it has a library-based design, which of course makes things like that somewhat easier. And that's kind of exploited within the LVM project to produce kind of beyond, initially it was just Clang, and even in the early days it shelled out to the GNU assembler. But building on a common set of libraries, you now have LDB, its debugger, LLD, the linker, things like libc++, newer sub-projects like MLIR, which we actually won't say much about today, but that's seen a huge amount of interest, particularly for machine learning type workloads. I guess another thing you might know about it is it's the primary code generation backend for newer languages like Rust, although there is work on adding support for alternative code generation backends like GCC or CraneLift. And the same is true of, in terms of LVM being the primary backend for Swift, Julia, Zig, and some other languages. And although your common Linux distributions are perhaps using GCC as their default compiler, it's widely used and distributed by many large companies, semiconductor companies and the like, as a default toolchain. So ARM moved over to that, as well as a number of others. Or it's used for particular projects, like the official way to build the Chrome browser and its subprojects and the same is true of Firefox, is with Clang, and so you actually have to go jump through some hoops to keep it buildable on GTC. In terms of LVM releases, it has a new release every 6 months, and it's just time-based. So if you're wondering what's going to be in the next LVM release, the answer is whatever's in tree by the time the release branch is cut. So we had a branching model every 6 months where new branch is created. We identify any regressions or bugs through the release candidate process. And then after that new release, so the most recent one I'm talking about today is LVM 19, there'll be different point releases, so 19.1.1, point 2, and so on, roughly every 2 weeks as any additional issues are found and addressed. Now, I'm kind of stating the obvious here in terms of what kind of changes might be in a new LVM release, but I guess the point I want to make is that through any project like this, any large engineering project, there'll be a whole mix of changes, some of them which are, huge. Every now and again, there'll be a big new sub-project or a major new milestone, things that are a little bit more minor, kind of new command line options, new features, new optimization passes, the more minor code generation improvements and bug fixes. And I'm kind of taking a bit of I mean, I wouldn't say it's not a random walk. I've kind of selected things which I think are interesting. I wanted to say a little bit about. It's kind of challenging to pick, I guess, things which I think are noteworthy within the latest LVM release, as well as things which also don't require a whole bunch of background to understand and introduce. But I'm trying to give a bit of a range of things from the big to the small that are interesting for different reasons. So let's step through and have a little look at the things I decided to highlight. So one area of one kind of direction of work that's been particularly interesting for me has been the increasing support for hardening options within sub-projects like libc++. One aspect of LLVM that you might know of is that it's home to tools like address sanitizer, thread sanitizer, memory sanitizer, all of these kind of opt-in debug utilities to help to find kind of safety or correctness issues with typically legacy C or C++ code. But an additional direction has been adding support for kind of a safer or checked mode of compilation for libc++, which is what provides things like your basic, string, stud string, stud vector implementation within LLVM. So the one of the newer features landed in LLVM 19 was the ability to produce bounded iterators for those core string and vector data types. So that is iterators where it will error at you if you go beyond the ends, rather than just it being undefined behavior and potentially being a memory safety issue. So it's not full memory safety. It is a spatial memory safety protection for a particular use case when you opt into it to opt into it. But in terms of it's another tool in the toolbox, and every little helps. A kind of funny point really is that it was actually only in this most recent release that C++17 support was fully finished in Clang. So I don't want to give the wrong impression. Clang is actually pretty good at keeping up to date with the latest C++ specifications. There was just one kind of slightly minor feature around some aspect of template handling that technically hadn't been finalized, and so this most recent Clang 19 release was the one that can finally tick the box and say everything in C++17 is supported. And in general, there's a pretty good web page, the one I linked to there, the C++ status page, where you can go through and see both the kind of finalized ISO standard C++ versions, as well as the ones that are still a work in progress. You can see exactly which proposals are implemented and which ones aren't. So WebAssembly has been an area I've worked in before. So this is a compilation target for the web. So it provides I guess it's often compared to, at least in terms of vision, compared to JVM bytecode, though it has kind of some fundamental design differences. The idea is that you have a low-level compilation target for the web, and that compilation target it moves forward a lot faster than the hardware targets I tend to work with. Unlike hardware, of course, you don't need to. You can move the specification forward just by looking to see, do all the major browser vendors support this new feature or not. And so there have been a couple of interesting new features there, particularly around reference types, which is what makes it substantially easier to interoperate with JavaScript, which were implemented and enabled by default in the default WebAssembly target. I said any new project, or any release, there's a range of changes, and so another one I wanted to highlight is the LLVM has a whole suite of tools actually, but so things like the static analyzer or Clang format to reformat your source code based on your project's preferences. It also has a coverage analyzer. So this is once you've compiled your code with some degree of instrumentation in order to see which lines are actually executed or not, you can then generate a nice HTML report and have a look at which bits were covered, which bits were executed and which weren't. And the report that's generated got an awful lot easier to work with in this release. Actually a relatively small change overall, but adding a little bit of JavaScript so you can easily flick between the next uncovered lines and regions and that kind of thing with some keyboard shortcuts. Now, the next one, I'm not going to delve into a huge amount of detail, but I guess the overall point here is that there's been a kind of long-standing work within LLVM to try and or as deficiencies in code generation are identified or spotted, sometimes that can be handled purely on the back end. Sometimes it can be handled on the front end, so generating slightly different intermediate representation. But other times the problem is that the intermediate representation we have doesn't allow you to preserve an important property from the front end semantics. So this was an issue that was identified, I think, first maybe a year and a half, 2 years ago. So the RSC I linked to is actually a follow-up to a previous discussion, and the issue was really around there are cases. So get element pointer is an intermediate representation instruction that's used to represent basically memory dereferencing. Suppose you're dereferencing an array or a array of structs. It's representing that in the at the IR level, but the uh, the possibility of wrapping either with signed or unsigned values, kind of the aspects of when that was possible or not weren't preserved through the intermediate representation, which of course means that some optimization opportunities are lost. So this was a nice cleanup to improve code generation in that area. Another pretty interesting kind of line of work to me is around the handling of debug information. So the mechanics of what's changed in the latest release are maybe a bit detailed. I can point you to that document there, which basically talks about how it's moving away from a representation as kind of separate intermediate representation instructions towards attaching debug information as values to the things that it represents. But it's quite an interesting problem because I think we're maybe all used to it being relatively easy to work on a piece of code, attach a breakpoint to a line of code that we're interested in, and it mostly just works. But of course, compilers are spending all their time working against this because when you compile a piece of code with optimization, you very much want it to transform your code, to make it faster, to mutate what your source input. And sometimes these transformations can be quite extreme, such that it can be quite difficult to figure out kind of how you map from your the code that you entered to the generated machine instructions. And sometimes you can just compile a separate version of your code without optimizations, and that'll work for you. But I think it's Sony and SN Systems in particular who have done quite a lot of engineering work over many years now to try and improve the handling of debug information for optimized code. Because of course, people who are getting a compiler toolkit and they're compiling a game, you may have issues that you can't reproduce when optimizations aren't enabled, or it may just be unusably slow to actually reproduce them. So that's a fairly important kind of use case for those people. I mentioned some kind of architecture independent changes on in terms of features for to protect against code reuse attacks, like return-oriented programming. For architecture-specific features, there's been work to further enable ARM support for pointer authentication codes. This is something that's been in kind of a range of uh, kind of ARM silicon for some time, but hasn't always, or at least the upstream LVM support for it has been incomplete, as well as things like the ABI. So fundamentally, the idea is that you have some hardware support for using otherwise unused bits within your pointers to contain a authentication code, which means that you have some degree of protection against that pointer being mutated by, say a spatial or temporal memory safety violation. And so that's got to a point where there's a full working ABI that runs under Linux that you can test and run if you have the appropriate hardware. This is kind of maybe not the biggest feature in the world, but I thought quite a nice one. There's a series of very, very low cost RISC-V microcontrollers. They cost around 10 cents, 10 US dollars, 10 US dollar cents in bulk, but you can buy from say European distributors a little kit. This is just €1 plus shipping, with this microcontroller implementing the RISC-V instruction set with some I/O, so you can do fun stuff with it. And yeah, someone noted that we didn't have support for for some of the additional custom compressed instructions that they added, and that was addressed in the most recent release. And also improvements in documentation. So this is some work one of my colleagues did, who's been doing a lot of work on RISC-V vector code generation. And if you go to this URL, you can find some fairly detailed documentation on exactly how this works and what happens. Now I know we're getting towards the end of the slot, so I'll just highlight a couple of additional things that I'm looking towards future releases as being pretty interesting. Firstly, there's one I forgot to mention at all, which is there's been a fairly long and still ongoing discussion about MLIR and its I guess ways of restructuring what's already in Tree and ways of managing it going forward. I think that'll be interesting. There's been a lot of work in recent years on Flang, which is a Fortran front end for LLVM, and it's now finally got to the point that the kind of prototypical project that they called Flang New can be renamed to Flang and advertised as, this is how you should compile Fortran using LLVM. And another pretty interesting line of work has been around support for offload. So if this kind of combines with work on LLVM libc, whereby you can compile a version of libc for, say, a GPU and compile somewhat standard code and then communicate with it using remote procedure calls. In terms of how to keep up with developments, we try our best to keep the release notes accurate. I think it's much improved with Clang in recent releases. There are some other sub-projects that maybe don't do the best job at this. So if you don't see any updates for a particular sub-project, it doesn't necessarily mean there haven't been any new changes. There's my weekly newsletter, or of course, there's LLVM's discourse. And with that, I may or may not have some time to questions, but I'll be around and can answer things in the chat. Thank you very much.
Thank you very much, Alex. I'm now here. I've got my proper name. The thing that says Embrycosm is actually me as well, and that's our corporate one. So thank you very much, Alex. There was a question on the chat from who's it from? Dave Donaghy, asking about what's the equivalent? I think effectively, what's the equivalent of GCC plugins for an LVM?
So I'm not actually familiar with what functionality GCC plugins offered. I think almost anything, but in terms of extension points for LLVM, most commonly you are either implementing your own pass at the II level, or there may be some external tool that passes LLVM AR, then does something with it. So so the thing with LLVM is it has a API you can use via the C++ libraries, but it's not stable from release to release. And so that gives a very strong incentive for people to upstream things. I don't know, Jeremy, given you're more of a GCC person, you might have more flavor on the differences for GCC plugins.
That's a very good point. I think, sorry, I've lost my control. Yeah, so my inclination is to say that GCC plugins are partly a history of the fact that GCC is structured away. And perhaps the easiest way to handle this is perhaps if Craig has a minute or two, just to touch on the plugin interface at the end of his talk. I think plugins are a historical relic. If you've got a nice library structured compiler written in a language, in an object-oriented language, some of what they do is perhaps not so relevant.
No, that's fine. That answers me certainly, because what you're saying, I think, is that actually for LLVM that question is moot, and I'm happy with that. I'll have a further dig around, but that's a good answer. Thank you.
Okay. Right. Thank you very much for the question, Dave. Alex is online, so ask him more questions in the chat if you wish to. I'd like to now ask my colleague Craig Blackmore to give a whistle-stop tour on how you add a new backend for your new chip to GCC. Craig, over to you.
Hello. I'm just going to try and share this.
While you're doing that, you may end up having to share my slides as well, and I'll send you the latest version.
Okay.
Because unless the BCS guy is still here, I'm actually not able to share slides as host because I'm here as Embrycosm. So there we go. But we will deal with that when we get to my slides.
Okay, are they showing okay for everyone?
Looks great.
Right. So yeah, as Jeremy says, this is a whistle-stop tour, really. This is an introductory talk to get you started porting GCC to a new processor. So let's dive right in. The GNU toolchain features many components. GCC is just one of them. There's the assembler, linker, and various libraries. This talk is only concerned with GCC. If you wanted to do a full tool chain, then you'd need to port all of the elements as well. But that's outside the scope of this. So what is the scope? So we want to get you up and running so that you know where to start. Firstly, introducing where to find different sources of information, and a look at starting to add some of the key elements for a new architecture, and debugging when things aren't working as expected. And the outcome is, as I say, you know where to get started. We're not going to build a new compiler in this time, but hopefully it makes it less daunting, and you'll know where to start. And you'll also get a glimpse of how of the anatomy of GCC. So I am assuming that people are familiar with GCC and compilers in general. I think a lot of the content doesn't necessarily need that much in-depth knowledge of actually using GCC, but we'll see. So sources of information, starting with the theoretical, there are some introductory textbooks. The one on the left is written by Jeremy. The one on the right, I believe Jeremy was recommended that, but I don't think we've read it. And then more comprehensive theoretical introduction, you have the Dragon book. The right-hand side is a lot cheaper. And then in the real world, the Bible, if you like, for GCC is the internals manual. And this document does a pretty good job of documenting how GCC works internally. We'll be looking specifically at the chapters most relevant to adding a new target. And a quick overview of the chip that we're targeting for this example. It's the Virtual Abstract Machine architecture, which is taken from Jeremy's introductory textbook. We don't really need to know that much about it for the purpose of this talk, other than it has 32 general purpose registers. If you were going to go ahead and complete the whole architecture, you obviously need a lot more detail. And the initial framework implementation, which Jeremy did as preparation for this talk, really, is on GitHub, available publicly. So this talk has been done in various incarnations of different lengths. This is, I think, the shortest version of it. So where do we start? The first thing you need is the GCC source, and you can clone that from the official repository. There's also an unofficial mirror on GitHub, which no one seems to know who the owner of that is, but it's handy because sometimes it will download quicker than the official source. So if you download the source, what do you get? The directory structure is as follows. You've got the top level GCC project. Inside there, the main GCC sources are in a subdirectory called GCC. And of most interest to this talk is you have a config directory where all of the target specific code is, or most of it. And there's a directory for each architecture. For example, RISC-V, AVR, i386, which will have all of the x86 stuff. And there's about 50 different architectures in there. There are also a lot of library directories. Most relevant to us are libgcc and the standard C++ library. libgcc provides low-level implementations of things that you maybe don't have support in hardware. For example, if you don't have floating point support, then you might get that from libgcc. There is more than this, and the full directory structure is in the internals with a bit more detail. So zooming in further, what do we have inside a target directory? The most relevant ones to get started with are these four. There are a lot more, but you'll get to those in time. So RISC-V.H, that's got various target macros that describe aspects of the target, such as the register set and endianness. RISC-V.C has target hook implementations. These are generally more involved than the target macros. So a target macro might just be defining some constant, whereas a target hook might have a larger function associated with it. And all kinds of supporting algorithms to tailor the code generation specifically for your target. So to tell GCC how to generate for your target. There's the machine description, and that describes all of the instructions that your target supports. We'll look at that a bit more in depth later on. And RISC-V.Op is where all the target specific options are defined. So if you've ever used GCC, you might be familiar with -m options, -machine options, and that's where those get defined. Okay, so if you're starting out with a new processor, GCC knows nothing about it. So if you try to configure for it, you're not going to get very far. So the very first step is to update the configuration. And there's a couple of steps for that, which are fairly straightforward. The first one is the configuration in the top level directory. This is maintained in a separate repo and then imported into GCC. But for simplicity, you can edit GCC directly for now. So it's just one line. We add vam, the target. Then in the GCC subdirectory, we have to add a vam entry as well. And this will cause allow us to configure GCC. GCC will assume that you're going to provide those 4 files that I told you about on the earlier slide. We also add the elf os header, and that defines some default macros for elf targets. So once we've done that, as a sanity check, we can try to configure the compiler. So let's make our build directory next to GCC, run the configure command. A couple of things to note on the configure command. There's our target triple. We're compiling without headers. So this means that we won't try to use headers from the target libc, which we haven't built yet. And we only enable the C language to reduce build times. There's a lot more configuration options available, which will allow you to enable, disable different things and other things. So the full information on that is in the link. So if we give that command a try, so we configure and then try and make all GCC. If you do make all GCC, you're only making GCC rather than all of the libraries around it as well. And we get to the point where make can't find vam.md, and that's not a surprise because we haven't created any of those files yet. But it tells us that at least we can now configure our target. So getting into some of the implementation details. Firstly, the header file. Well, let's start by adding empty versions of the missing files and then do another run to see if we get further. A lot more happens this time, but then we see that we're missing one of the target macros. So that happens to be the first target macro that GCC tries to use. We'll actually define that later in one of the later slides. So we've put it off long enough now. We better get into the detail of how we implement the guts of the target. Much of the work will happen in vam.h and vam.cc. So what needs to go in here? Well, there's a very good chapter on this in the internals. Pretty comprehensive, but it is unfortunately 200 pages long. I would suggest the proper way to go about this is to read through all those and identify the macros and hooks that are relevant to your target. There are probably going to be a lot that you don't care about necessarily, and some of them will be for optimization. So if you're trying to get things up and running to start with, then you don't necessarily need to worry about those straight ahead. So identify the relevant macros and hooks, and then you can refer to existing targets for how to actually implement those. OR1K is a good example because it's a fairly simple port. So we won't have time to get too deep into this, but let's have a look at some of the initial macros that we might add to vam.h, and those will describe data storage, data types, and register model. There are other essentials that we're missing here, such as stack layout, calling convention, addressing modes, and each of these have a section in the internals that go into detail what you need to do. So storage layout, this is straightforward, really, not very exciting. Sizes of things like words and pointers and different alignment requirements or preferences. This is slightly more interesting. Sizes of different language types. How long is an int and a short? Interesting note here is since this demonstration was made, since this slide was written in February, 3 of these target macros got removed upstream. So if you did try to rebase this on top of the latest GCC, it wouldn't build anymore. And that just shows that GCC is a moving target, and it's hard to keep tutorials like this up to date. Moving on, registers. We've got a comment just explaining what registers we have. The key takeaways here are we've got 32 general purpose registers and an additional status register. How do we define those? Again, with target macros. This is the missing macro from earlier, first pseudo register. This tells you where the real registers end. So yeah, we've got 33, 0 to 32 registers. I won't go into too much detail about the significance of pseudo register, but if you look in the GCC internals, it explains that target macro. Register names then, that defines, as it says, the names of each register, and then corresponding to the indexes of that structure, we also define which are the fixed registers. And these are ones that the register allocator is not allowed to use for general allocation. Register 1 is fixed to 0. Register 0 is fixed to 0. Register 1 is the stack pointer, so we don't want that generally available for allocation. And then the final register is the status register, which is also special. We can also define the order in which GCC will try to allocate to each register. And again, that's referencing the indexes from the previous structure. So we've got our registers, and there are also register classes. This isn't that interesting for this architecture because we've only got general registers and the flag register. If you've got floating point registers, then you'd have that as a separate set, and this allows GCC to distinguish between instructions which can take general registers or floating point registers. And register class contents is a bitmap of the membership of each register. Conscious of time, so I'm not going to spend too much time on that, but and we've also got a lookup for the register number for each. You can take a register number and then look up the register class for that number, for that register. There's a lot more than that, and you do need to add other target macros before the compiler will even build. It's outside the scope of this talk, but you can see the implementation on GitHub or other backends. Adding implementation. So now looking at the machine description, which is a major part of the target, this describes the different instructions that GCC can generate. So GCC's got 3 main intermediate representations. In order, they are used broadly by generic is by the front end, Gimple by the middle end, and then RTL by the back end. And when you're creating a new target, you're most interested in RTL, and this is close to assembly level. Optimization happens on Gimple with tree transformations and on RTL with RTL transformations. When you're starting out with your target, you're most interested in telling GCC what is the valid RTL that it can generate for your target. And we're concerned with how does GCC lower Gimple to RTL. GCC has a set of standard patterns that it understands for different types of instructions, like adds and subtracts of different sizes. And our job in the machine description is to provide templates telling GCC, making those instructions available to GCC. There is a set of these that you must define, but as far as I know, that's not written anywhere. It's not written down anywhere which ones, what the minimal set is. But for example, you'd need to have addition and multiplication in there. And there are a lot that might not be relevant to your target, for example, vector operations. So I have an example of machine description. I think I'm going to run out a little bit of time to go through that. But if I give you the overview, so this is an example of what you would put in the machine description. So we're defining here an add SI. So this is an add single integer, which is a 32-bit add, and we're adding operand 1 and 2 and storing the result in operand 0. When GCC is optimizing it, during each RTL pass, you'll have your code will look something like this. It will be an RTL form, and then after you finish your last RTL pass, then you need to convert it to assembly, and that's what this line here is doing. It's telling GCC how to get from the RTL version of the instruction to the assembly version. I will skip a lot of the detail of that, but most of this here is telling you what is a valid operand. So it has to be a register. But the second operand 2 can be a register or an immediate. And we can define this start defining patterns for our own target as well. So our adds are quite similar, except for the target only has 2 operand instructions. So there's a constraint here, which is telling GCC that the second operand needs to be the same as the first operand, operand 0. And much more information on all of this in the internals manual, particularly those sections. Putting it all together. So there are extra things we needed to do that there was no time for in this talk, but is in the repo in order for us to build GCC. I won't run through those, but you can have a look through that. And where we get to eventually is if we try and build the compiler again, then we hit an error because we're missing a target hook. That might need some investigation if you're not familiar with that message, but we're missing target legitimate address _p. There's advice on how to debug GCC. So you can debug GCC with GDB by using the wrapper option, which will prefix all the commands that GCC runs with GDB. There's some options for dumping internal state. If you do have a compiler that's building stuff and you want to see how things look after each pass, you can also annotate your assembly to see how it relates to the RTL templates. So what's next? Well, there's still more to do. As I said, we don't have our calling convention yet, for example. So keep working through those target description macros and functions in the GCC internals. And this is part of our 3-month graduate training course. This section is given over 5 days, supported by exercise, but today we did it in nearly 20 minutes. There's a related talk by David Malcolm from that was done at FOSDEM, which is also a good introduction to getting started developing GCC, but not necessarily for a new architecture. And in the meantime, you can have a play around with and extend Jeremy's initial framework port there. Thank you very much. I don't think I have time for questions. I think I've gone over, so I will hand over to Jeremy.
Thank you very much, Craig. Craig, if you look on Mattermost, you'll see I've sent you my latest slides. Could you display them, because I do not have the power to share them, because the technology has failed us today. So if you put the slides up, and I'll just say next as we go through them. Thank you very much indeed, Craig. And there is a pretty lively discussion going on in the chat. A lot of questions asking how you could do exotic architectures, and I've drawn attention to the fact that Lewis Revel did a version of LLVM that would compile for the Apollo guidance computer, which has 15-bit words and no registers. So with a bit of effort, you can make LLVM do just about any weird architecture you think at. And though it's well known for its doing mainstream RISC architectures, ARM, x86, well, x86 isn't RISC architectures, but ARM, RISC-V and so forth. It also does things like GPUs, and we'll look at some others in this talk. Okay, so keep the conversation going there. Craig's recommended the Open RISC backend for GCC OR1K. The guy who wrote that really knows his stuff. It's quite simple, it's quite clear, so it's a very good starting point. And everyone does their GCC backend by copying someone else's and then modifying it. No one does it from scratch. Okay, right. So I just want to wind up. This is just a short talk. It's a whistle-stop tour through all the different other open source compilers. And I'm barely scratching the surface here. These are just ones I know about, I've had a play with, or I know the people who worked on them, or they're historically significant. But there are oodles of them out there. And I changed these slides while Alex was talking, because he mentioned a couple I'd clean forgotten about that I thought wasn't on here. So next slide, please. Craig? That's it, yeah, okay, bit of lag there. So we'll basically look at what other front ends there are to GCC and LLVM. And so those are the compilers we've already seen, but there's a whole host of languages they support. We'll look at compilers. It says derived from GCC and LLVM. It really means derived from LLVM, because if you want to do a new compiler, everyone starts from LLVM. It just is more modern. If you're going to do major surgery, it's probably going to be an easier starting place. Then we'll look at other C and C++ compilers, because though GCC and LLVM dominate, there are a number of other open source C compilers, some of which are of particular interest. And lastly, I'll romp through one or two open source compilers for other languages that I think are fun. Okay, next slide, please. Next slide.
I think there's a lag. Is that showing now?
Not yet. No, it'll get there. I'm sorry for this. I'm still seeing the title slide. That's it. Oh, next one. That's it. Right. Okay. So I'm going roughly into it. So NAT is the GNU Ada compiler. It's part of the GNU distro. It's in tree. It's part of the standard distribution. It's maintained and developed commercially by Ada Core. They've been around for 40 years. They're about the only open source compiler company older than my company now. It's the industry standard. If you fly in a jet plane, the code that controls the engines will have been written in Ada, and it will have been compiled by NAT. It's a rock solid compiler. They are ferociously dedicated to open source. They push all their stuff upstream. Great company, great compiler. GCCRS, my colleague Arthur Cohen leads that project with help from Pierre-Emmanuel Patry and Philip. I've got Philip's surname now. So three of them driving that, but with a huge contribution for other people in the community. It's still experimental. It's in GCC 14.1. Full release where it stops being experimental is expected in GCC 15.1. Getting it to the stage where it can do Rust for Linux support, which is the subset of all the Rust crates you need and versions you need for Linux. And with a proper borrow checker, that's likely to come in GCC 16.1. At the moment, if you want borrow checker facilities, you have to do it with the standard Rust compiler and then put it through GCCRS. That's a very actively developed, very lively project, does a lot of Google Summer Code work. If you want to get involved with compilers, it's quite a fun one to get involved with. Very active and supportive community. Next, please. GFortran, GNU Fortran compiler, supports up to ISO Fortran 2008. It's very widely used in HPC. And those HPC machines cost millions, tens of millions, hundreds of millions of pounds or dollars. And that compiler is maintained by 4 volunteers. And I know from years ago, talking to the people who do the UK's HPC infrastructure, a third of the software run on those £1 billion worth of investment by the British government is run with GCC, maintained by 4 volunteers. So I'm making a point there. GCC Go, that's a Go compiler using GNU. It's not the same as, it's an alternative to the standard Go compiler. It's still actively maintained. Ian Lance Taylor heavily involved in bringing that together there. Next, please. The Modular 2 compiler. So that supports a lot of standard modular. If you like Modular 2, the sort of child of Pascal, then that's a good compiler. It's been the long-time work of Gaius Mully at the University of South Wales. He speaks on it each year at the GNU Tools Cauldron. So great piece of work. I'm sure he'd welcome anyone else who wants to get involved in maintaining that. The GNU D compiler, for those of you who like the D programming language, there's a community of volunteers that have the GNU. That's still under development. I think one of the things they're particularly appealing for is help with the documentation. Next, please. And lastly, Objective-C and Objective-C++. These are extensions for C and C++. They were the in-house languages used by Apple. They're now largely obsolete. They're not a separate function. They're really parameters that you control when using GCC or G++. So those are all interesting. If you download standard GCC and you compile all languages, you'll get all of those. Next, please. Front ends out of tree. COBOL. COBOL's really exciting. COBOL is one of those fields where the open source world has only had a minor impact. Someone told me the British Home Office spent 5 million a year on COBOL licenses to HP, what used to be HP Enterprise. And if you give me 5 million, I can take these GNU COBOLs up to anything that'll match those. So the open source world hasn't yet, but COBOL works, and other companies are doing a great job pushing open source COBOL out there. The technology is great. When I teach COBOL, and I do teach all sorts of weird languages, I actually use GNU COBOL. GNU COBOL compiles to C. It's a separate compiler. It's not really a front end. I put it only under this thing because GCOBOL is a true front end to GCC. It's still under development. They'd welcome anyone who wants to contribute there. The hard thing with COBOL is, yes, it's an ISO standard, but actually every manufacturer extends it. So you get the COBOL for the particular manufacturer. So there are loads and loads of non-standard extensions. And the big challenge for GCOBOL is to support all those. So it can be a drop-in replacement for commercial compilers. Okay. GHDL, been around for a long years. It's a VHDL. VHDL is a language used for designing silicon chips. And it's a front end to GCC, so you can generate C code you can then compile to give you a simulation of the chip. It's been maintained for years by Tristan Gingold, used to be at Adacor, he's now at CERN. So yeah, great project there. If you're doing chip design in VHDL, you will know about GHDL. Next, please. Okay, loads of other people have done GCC front ends. Lots that are no longer maintained. There's the GNU Pascal compiler, but no one's. It's on GitHub. You can find it, but it only works with GCC 4.6. I think it has nothing done to it for 13 years. PL1 GCC for people like PL1. Mercury was an experimental language, I think, from an Australian university. No work on that for years. GCJ, the GCC Java compiler, that used to be part of the official distribution, but it got dropped 9 years ago. And there's many others that people have done over the years, but these are some ones that you might have come across. Next, please. LLVM, let's let them look at LLVM. Alex mentioned Flang, that's the LL Fortran front end, and it's aimed at supporting Fortran 2018. That's a huge standard. It's been going on for years. There have been great teams from ARM and others developing that. It's many years in development, and it's not to be confused with Classic Flang, and I'll talk about Classic Flang in a moment. But Flang is a major and active project in LLVM. Next, please. Classic Flang. Well, a Portland group, about the time they were acquired by NVIDIA, donated their old Fortran front end to the GNU project to use as a front end for to the LLVM project to use as a front end, which is great. Except the reason they were happy to do was that it was a very old front end, and it was not going to be any use to be 2018 support. So they knew they were going to have to write a brand new front end. So they open sourced the old one, and that supports up to Fortran 2008. It works today, and if you want an LLVM based Fortran compiler, that works. Okay, there's a few hoops to jump in to build it, but it's known as Classic Flang, but it will be replaced with the new Flang when that's ready. And then there's things like the Rubinius compiler, which is a JIT compiler for Ruby as part of the Rubinius project. There's LLGo, which is a Go front end for LLVM. It's tied into the Go++ teaching project, which is a weird sort of view of how you should teach children programming. I don't entirely agree with it, but yeah, great that people are trying to teach people interesting languages. Next, please. Swift, mentioned by Alex, Apple's named programming language. It's largely replaced Objective-C and Objective-C++. Julia sort of comes from that ancestry of scripting languages. Maybe it's a successor to the likes of TCL/TK. And Zig, that's a lightweight replacement for C. So lots of them there. Next, please. I don't know why there's no title on that slide. So those are the front ends on there. Let's look at other ones. Plan 9 C compiler, very lightweight compiler. It's incredibly small, a few thousand lines of code. Only supports unoptimized C90, but you can bring it up in a flash. And I think if you were to go to someone like Richard Miller and say, who's the expert on this, and say, can I have a new C compiler? He'd probably give you something in a few weeks' time. There's a previous BCS talk from one said Richard Miller, who used to be treasurer of this group. It's online on the Open Source Specialist Group YouTube channel. It's the third most viewed BCS OSSG video of all time. He's a very good speaker. Next, please. SDCC. This is the other one you may have come across, the small device C compiler. On the whole, GCC and LLVM don't get involved with proper 8-bit. They do for Atmel AVR, but most 8-bit compilers aren't supported by GCC or LLVM. SDCC has always had that niche for things like 8051, 6502, Z80. Tiny, not just tiny little 8-bit compilers, the sort of thing that might be controlling your fridge temperature or something. And there's billions of these chips out there. So SDCC stands for the Small Device C Compiler, but it was created by Sandeep Dutta, so maybe it was Sandeep Dutta's C Compiler as well. Really interesting thing about it is register allocation is a known NP hard problem. So GCC and LLVM use heuristics like register coloring to try and do register allocation. Because these programs and their chips are so small, SDCC does a full optimal register allocation. And although it's NP complete, NP hard, it's still small enough. It gets it done in a reasonable time. Okay, and it hasn't got as many optimization passes as say GCC or LLVM. I mean, GCC's got over 200, but it's got quite a few optimization passes. Very interesting little compiler there. So recommended you. Next, please. Tiny C compiler. It's written by Fabrice Bellard, the guy who gave you FFmpeg, the guy who gave you QEMU, and in his spare time set the world record for the number of digits of pi computed. So since he wrote it, it must by definition be good. It's a direct C to x86 compiler. You can run it as JIT. It's got no intermediate code, no separate assembler and linker. He did it years ago. It's still absolutely fine, but he's not developing anymore. But when he compared it against GCC3, it was 10x quicker. GCC has not got any faster. So I suspect it's even faster now. So if you want a fast compiler that goes very quick, and it's only for x86, go and have a look at that. The portable C compiler, that's a very early C compiler. It comes from right from the beginning of C in the 1970s out of Bell Labs. It's now BSD licensed on GitHub. That's there of historical interest. There's actually, I think, a version of that that's the original source code, and then there's a version that's a bit more up to date. Next, please. Okay. So compilers, now these aren't just front ends, and I think I distinguished it because some people have LLVM as the engine, but they've got more than just a front end. So Rust is the official compiler for us. It's based on LLVM, but it's much more than just a front end. It's got the borrow checker to enforce the memory safety features and an extensive runtime system to manage all the Rust crates, and it's maintained out of tree. Next, please. AI tooling. So this is something that's interesting. So let's just look at neural networks. This is how all neural network systems, PyTorch, TensorFlow, JAX, Open Neural Network Exchange, all work the same way. They represent their neural network as a graph, and they're fundamentally interpretive. You walk over that graph and evaluate the nodes, and the nodes will say, do this operation on these arguments, which are tensors. Tensor is just a fancy name for a matrix. And you walk over the graph, evaluating these operations, that will do your inference or your training. Okay, and it works in an interpretive way because the operations are relatively big. And the mode of operation is a host and accelerator view of the world, where you look at these operations and you have a dispatcher that says, put it on a host or put it on the accelerator. And that's how all these AI systems work. Next, please. And then, clever people have said, well, simple translate, maybe we can do things with a neural network to make it easier to compute. And so there you have, used to have Apache TVM, that's still around, it's quite old, that's a sort of compiler. Interesting one I'll talk a bit more about is OpenXLA, which is an LLVM compiler. Okay, so if we look at that, next slide, please. Places where you can do interesting things with compilers are in the dispatcher, and we'll look at that in a moment. And next, please. And in the graph level transformation, we'll look at that. Next slide, please. So if you've got a high performance accelerator, so a big GPU, or people are making these 1,000 core RISC-Vs and so forth, a simple sort of serial loop is not going to be terribly efficient. So you have languages like SYCL and OpenCL, which are extensions respectively to C++ and C. OpenCL has been around for 2 decades, originally designed for graphics programming, a bit like CUDA, but eminently suited, and they are very good at describing parallel operations. They can tell you how to break stuff down so it can be done in parallel, and they can tell you things about promises of results. So go and do this, and here's a handle to give me the result when you've got it available. Okay, so both OpenCL and SYCL, they are modified LLVM compilers that take those languages, and they will typically generate for this world an interesting binary, because it's a multi-architecture binary, something to run on your host and something to run on your accelerator. So something on your x86 and something on your GPU, or something on one core and another on a different core. Okay, and various ways of implementing that. You can bring it up in about 3 months to make it go really fast. You're going to probably want several years. Next, please. So that's the dispatching side of it. And then when you look at optimizing the graph, this is what OpenXLA and its associated IRE, and IRE is very, very new. It's still alpha mode. It's the alpha stage. So your neural network you represent as a graph in a language called stable HLO, and you transfer it into one of these multi-level IRs that Alex touched on, which is one of the internal representations inside LLVM. And then you have a series of LLVM passes, one to do graph optimization, another to do mapping to your device, so partitioning half matrices so they fit your matrix multiplier, and then into standard LLVM code generation, and you get your multi-architecture ELF, some to go on the accelerator, some to go on the host, and the runtime library from OpenCL and SYCL, say, to close it and control it all. So that's a really interesting LLVM compiler. Next, please. Yeah, and just others open source compilers. Verilator, that's a Verilog or system Verilog C++. It's very like GHDL, but for Verilog. It's interesting. It's completely it's a tree-based compiler. It generates an abstract syntax tree and a whole set of passes that manipulate it until that tree looks like C. And interestingly, for those of you familiar with patterns, it uses the visitor pattern as a regular structure to control its passes. Okay, next, please. Phil Budney's, I presume Phil B isn't Phil Budney, but Phil Budney's written this really rather nice Snowball 4 compiler. Snowball 4 is a string processing language developed in Bell Labs. Spitball was a compiled version of that from Robert Dewar, same Robert Dewar who co-founded AdaCore. And then the Snowcone, which is a derivative C-like language front end to Snowball 4. And you can even actually have Snowball Python. There's a package to add Snowball 4 bead diagrams. Snowball 4 bead diagrams are the clearest way of expressing regular expressions to match strings, or not. They're richer than regular expressions. So I quite often still use Snowball 4 when I've got complex text processing to do, rather than spend a whole day wondering why my bloody regular expression doesn't work. And Phil Budley has written a rather nice Frost Snowball 4 compiler, generates C code, which is then compiled. Okay. Next slide. More open source compilers. UCSD Pascal, very popular in the 70s. It's now been open sourced by University of San Diego, and so you can get hold of the source code for that. And lastly, GNU Sim, an implementation of Simula 67. Simula 67 was designed for event-driven simulation, key influence on other languages. Everyone knows that C++ came out of C. What a lot of people don't know, it came out of C and Simula 67. Simula 67 is where all the ideas for classes and objects came from. And for those of you who use coroutines, you saw it here first in Simula 67. And if you ever use System C to do hardware chip design, you will effectively program Simula 67. So thank you very much. That was my last slide. I'm not sure who took it away or whether the system has done it automatically because we got to 9 o'clock. Thank you very much. There's all sorts of questions going. I hope you've enjoyed that whistle stop tour, and it's given you some ideas for languages and compilers you might want to look at. I'm happy to take a question or two until we get shut down. Okay, if anyone's got any questions. Is super optimization a thing for 8-bit? Yes, I've done super optimization for AVR, and you can. Super optimization is this idea of not just making code better, but asking the question is, what is theoretically the best translation you can do? It's an exhaustive search. There are some approaches using symmetric modulo theory solvers that you can use as well, but they are all at least NP hard solutions. Typically, you'll be able to sort of optimize 10 or 15 assembly instructions, but it can be spectacular. Wei Ren Chen's got his hand up. Wei Ren? Hello, Wei Ren, you're muted. Okay. Wei Ren seems to have put his hand down, so maybe that was his question. Oh, no. Anyway, question, is anyone doing any work on Smalltalk? I'm not aware of anything, but yeah, great. Early object-oriented language. Very interesting ideas in it, coming out of Xerox PARC. If I think I got that right. Yeah. Any other questions? Okay. Well, if that's it, thank you very much. The BCS Open Source Specialist Group talk series is back up and running. Dave Pearson's been on the talk all along. He's our new chairman, doing a great job in getting us all going. If you'd like to get involved, reach out to David, reach out to me or any of the other speakers. We'd love to have you involved in putting together more talks. David, if you want to unmute, can you just tell us about upcoming meetings we've got?
Can you hear me?
Yeah, got you there. Yeah.
Oh, splendid. All right. Well, first of all, Jeremy, thank you so much for actually kicking off the new webinars. Very, very interesting information. And actually, thank you to everybody else that's actually given up some time this evening to come onto this webinar. In terms of moving forward, the next one will be in a couple of weeks' time on the 5th of December. There's actually a hybrid event taking place. So I'm actually going to be at my local BCS branch in Kent. Hopefully you can register to join by Zoom as well. And I'll be talking about ethics and open source. And I'm hoping to get other events lined up very, very quickly. Obviously, we've got this thing coming up called Christmas, so we may have to take a little bit of a break. But if you please keep posted, particularly in our LinkedIn group that we've set up, you'll start to see that there'll be more webinars coming soon. With that, I can see that we've probably pretty much run out of time.
Yep, okay.
So thanks everybody for joining, and hope to see you on the next call.
And thank you to Craig and Alex for their 2 talks. I've got to call you out, but great from that. Dave, very quickly before we get kicked off, Dave Donaghy.
Oh no, sorry, no, that was applause, not hands. That was just applause.
Oh, right, okay. Okay, yeah,
Thank you,
fine,
though.
okay, right, fine. Well, thank you for the applause. Yeah, okay. So see you at the next talk. And I think all being well, there'll be a talk on AI on the 16th of January as well. But join the group, watch the website to see when that comes up. Bye all.
Thanks.